So we move to the last talk of the conference. It will be given by Professor Ohno, and we will learn about 2 and 3 terminal spintronic device for very large scale integration, progress in spin orbit torque devices.
Well, thank you very much for the introduction, and I would like to thank Stefan and organizers for giving me this wonderful opportunity to be in CIN. Today I will focus, although my title is general, I will not focus on 2-terminal devices because it has already been covered by many. I will be focusing on progress in spin orbit torque devices, particularly from the VLSI perspective. These are my collaborators, and I've been supported by 3 different government programs. Okay, what we believe is that we also have to do similar things that semiconductor people are doing. We have to go for dense memory, and we have to go for fast memory, but we have to do it in separate configurations. So these are for DRAM, these are for SRAM. And for density, we need to go to 2-terminal, but for very fast switching, we believe that 3-terminal has an edge. And although we've been working on the minimal 3-terminal motion devices, today my focus is on spin orbit torque switching. So we already know that running current in a heavy metal can exert the torque that you place torque on a ferromagnet that you place on top of your heavy metal. But there are 3 different ways to configure. So this is one way. We all know that the first realization or demonstration of this is being done by Grenoble Barcelona collaboration. And so running current in X direction, and you have magnetization perpendicular to the plane. And this is Cornell-Isaka version. You have magnetization in plane, but perpendicular to the current direction. Current direction in this talk is always in the X direction. The third possibility and the last possibility is that you run current in X direction and you have in-plane magnetization, but you have your magnetic easy axis is collinear with your current. And this is a macrospin simulation of what happens in terms of switching. These 2 cases we need magnetic field to assist, otherwise we will not have deterministic, so-called deterministic switching. This is exactly the same as STT in 2 terminals, so we do, I will not go into the detail, but basically it's field free, and at high switching speed, as we learned from earlier talks, that threshold current is inversely proportional to the switching speed. So from the trajectories, this is basically precessional switching. So we expect it to be fast, so the question is, what determines, how much current do we need to invest in order to see this fast switching? The second question is it really fast? And the third question is perhaps that we don't want to have this magnetic field always applied to the device, so we want to remove this this HX or HZ. That's already been discussed as well. All right. So first, threshold current. So we've been making, this is type X, from cobalt ion boron on tantalum. So this is good because we can also make type Y and type Z. Type Y is Cornell, type Z is Grenoble, Barcelona. So this is the dimension that we've been working on this type X. And the slide here just shows that indeed we can have magnetic field switching as well as current-induced switching, and the sense depends on the polarity of the field that you apply in Z direction. And it's consistent with the fact that Tanton Hall angle, spin Hall angle is negative. So, so basically we can have full swing switching with magnetic field and also current with assisting magnetic field. So we can, as I said, we can also make type Z and type Y from the same material set like this. So this is type Y and this is type Z. This is, let's say, we have 40 nanometer diameter. I will vary this later on, but this typical example is for 40 nanometer diameter device. This one, the good thing is that we can get this device from exactly the same wafer. So the only thing we did was to just rotate the easy axis for, let's see, 90 degrees. So, and we managed to have very similar E over kBt energy barrier. Well, these two are not of any surprise because we're making basically the same device, but with 90 degrees rotation. The threshold current, experimentally observed for this one is approximately 1 times 10 to the 11 amps per square centimeter. And this is comparable to what you would expect from known, let's say, spin Hall angle. So this is no surprise. We get from type X and type Z threshold current of about, in this case, 20 times this unit, 4.3 times this unit. And actually, assuming this spin Hall angle, we get actually, we should expect much larger threshold current if we only assume Slonczewski torque. In other words, in order to explain these numbers from let's say from known expression, we have to assume that the spin Hall angle is actually very large compared to this type Y. Although the measurement, independent measurement shows, well, there's already a factor of 2 or 3 difference, but here another factor of 4 difference. Well, this cannot be true because we're using the same material. And for this case, the same wafer to make these junctions or these devices. So in order to understand this, we went through, we first concentrated on type Z, which is perpendicular. And we measured, we varied the diameter of the device and made sure that the big device shows extraordinarily small threshold current, but smaller device that is smaller than 100 is basically somewhere around 2 to 4 times into 12 in this particular case. So, for example, concentrating on this guy, the threshold current is about 3.5 times into 12 amps per square. So these are different devices than previous one, but the characteristics are basically the same. So let's see what happens with this one. So this is an analytical expression only considering Slonczewski torque. This means, and we know that from the transport measurement, the spin Hall angle is somewhere around here, and we know that our threshold current is here. So it's way off. So we need to understand what this is all about, and you might already have suspected, we need to include the field line torque. And we know from the same measurement that we have 2 times larger field line torque than Sonchevsky torque. So let's try to see if that explains, or at least that brings our numbers closer to what we have seen. So from transport measurements, the field line torque is twice as large as the Sonchevsky torque. And we had to go through a numerical calculation, although this is a straightforward macrospin calculation. And the agreement is much better. 3.5. This is our experimental result, and this is what we expect from our transport spin Hall angle. This is the spin Hall angle measurement, and the result appears to indicate that the spin Hall angle is somewhere down below 0.1, maybe 0.06 to 0.07. So we believe that you have to take into account, in order to understand the switching threshold characteristics or current, we have to include the contribution of this field line torque. Okay, so that's one thing. Another thing is that we're studying this because it's supposed to be fast. So let's see if it is indeed fast. This is 2-terminal case. We already saw this this morning from Andy Kent's talk. These are 3 different devices, but here it says this is more or less universal, that there's threshold current depends on the switching speed or your current pulse, and when you go below, let's say, 10 nanosecond, it increases as has already been mentioned. So this is something that we don't want, because in order to make it 10 times faster, we have to invest 10 times larger current, which is and you can go very close to the dielectric breakdown of MGO. So in order to get reliability there, we cannot run very large current through this insulator. So this is a problem here, and that's something that we would like to see if we can overcome with spin orbit switching. So simulation shows, this is comparison between type X and type Y. Type Z is very similar to type X. Although we need some magnetic field here, it says that initially the switching needs a little bit more switching current, but as you reduce your pulse width, it doesn't have the steep dependence, which is proportional to one of our pulse widths. So what we would like to see is if this is indeed true or not. And there's a work done by ETH group. They're saying that this is type Z, so it should be similar to type X with a fast switching. But unlike what people have expected, actually the switching current increases as you lower the pulse width. So we wanted to see if this is indeed the case. And again, I just want to emphasize that we are making type X and type Y from the same wafer. The only difference between the two it's just rotated 90 degrees. And this shows a switching probability as a function of current density with 1, 2, 3, 4 different switching pulse widths. So at the slow or long switching pulse, type Y, the STT-like switching, switches very at low current density as expected. But as you shorten your pulse width to 10 nanosecond, 1 nanosecond, and 100, let's go on. So 500 picosecond, you can barely see switching in type Y, but you can still see the very similar current density, switching current density for type X. So this is what I actually expected from simulation. So we believe, although this number is still large, 3 times it's 11 amps per square meter, it scares VLSI people off, but this constant current, switching current is down to 500 picosecond. It's a very encouraging sign that we can go to high speed operation without investing too much current. And in order to reduce the switching current density, for example, we all know that there are materials that can give you higher spin Hall angle, for example, tungsten. And this is tungsten channel, and this is tantalum channel that I have just shown. So at 500 picosecond, we can reduce the threshold current by, well, let's say factor of 2 or so. And this 500 switching, although the number is not large enough, but we see 0 error rate. So 500 trials have all succeeded in switching. So this is an encouraging sign, and the threshold at the moment at 500 picosecond is, well, slightly below 2 times 10 to the 11 amps per square meter. All right. So now the problem, the third one, is field-free switching. We want to get rid of this field, and how can we do that? So this is what we got. This is our favorite type X. But here we need, as I have shown, magnetic field in Z direction. But I've also shown that if you rotate 90 degrees, we get field-free switching. So why not just slightly tilt this one, so that we can enjoy the field-free switching in addition to the fast switching. Although we haven't, the work is in progress, but the simulation, at this macrospin simulation, shows that even tilting 1 degree will give you field-free switching. And 15 should be good enough, and 25 is there. And the speed is, at least up to 25, the speed is almost the same as the one that we see in with magnetic field. So we try this. And as you can see, this is 0 degree no tilt, minus 15 degree tilt, 15 degree tilt, and you can see that 0 magnetic field in Z direction. We observe field-free switching with sense depending on which way you tilt. So this is good news in a sense that we can stick to the same material set. Of course, the energy barrier that we see in this system is not good enough, high enough. But we can engineer many things with the same in-plane configuration. The reason why I said good news is that we can work on basically the same material set. And that means that in order to develop etching technology and other technology for VLSIs, we cannot change the material set very often. At least for several generations for the size that they're working on, we would like to stick to one material set. And this encourages us because we're using the same old cobalt ion boron MgO. All right, but in spite of the fact that people in technology domain likes to stick to the same material set, we actually deviated from that and tried something else. Removing this field that is necessary by antiferromagnet. We've seen already a number of times this figure, so I will not go into detail, but basically what we wanted to do is to see if we can exchange bias this thing and also get a large enough spin Hall effect from this antiferromagnet, so that we can switch ferromagnetic layer we placed on top. And there was an encouraging sign here that the inverse spin Hall effect is large enough in those antiferromagnets, so we went ahead and using this 5-layer system. And this is the detail of the structure, but we used platinum manganese with 60% manganese, and depending on the thickness and based on this annealing condition, as Eric mentioned, 300 USC 2 hours, 1.2 Tesla, we get no bias on 6 nanometer thickness of platinum manganese couplers, but a good exchange bias of 8 nanometer thickness here. So we can get two versions, two device sets from the same material stack with and without exchange bias. And here is a device. This one actually is a very large device, 10 micron by 100 micron. And we used the anomalous Hall effect to see if the devices switch magnetization. So what we get was with no bias, so there's with the absence of exchange bias, we had the difficulty observing current-induced switching at zero magnetic field. But with bias 8 nanometers stack, we can see, although it's very difficult to see in yellow, a nice switching characteristics. And we need to compensate the exchange bias, exactly the exchange bias that we see in the system, in order to get to this non-switching mode. So this is a measure actually of the exchange bias that we have. So it says two things. Exchange bias works in place of magnetic field that we applied, and also this platinum manganese has reasonably large spin Hall angle, so that we can switch magnetization back and forth. And the current, at least in this level of 10 milliamps, this is about approximately 10 amps per square meter, so it's comparable to other devices as well. All right. And in addition, in addition, we have observed an interesting possibility that we would like to pursue is that we can actually select the level of reversal by how far you go with your channel current. So when you go full swing, then you get full reversal, but when you're half there, you can come back with half magnetization. Of course, it means that you have many grains, and it's the grain statistical reversal grain you can control with this range that we apply with this current, and these are the same device and without magnetic field. So it appears to us that at least it might work as an analog, non-volatile analog memory, which might be useful for neuromorphic computing. So I guess I'm 30 seconds. Okay, all right. So basically, you have seen this once again. Once again, I'm going to show you. Today we have this speed gap between DRAM and SRAM, and also DRAM and hard disk drive or NAND flash. And we are hoping that we can, with this 300 devices, we can get this gap removed. And with other technologies, the Spintronics-based technology, we are hoping that in the future we get higher performance with greener, less power. So with this, I'd like to thank your attention. Thank you very much.